So this is the last presentation. It's always difficult to be the last speakers, especially when you had such great presentations before you, but we will try to do our best. So we will be having a presentation that is very hands-on. It will revolve around debugging planning issues using Calcite's built-in loggers. So presentation is from myself, Alessandro, and it's shared presentation with Stamatis. So the outline of the presentation is as follows. We will provide some motivations to take an interest in built-in loggers, showing some common planning issues. Then we will deep dive into the built-in logging system in Calcite. Then we will showcase how to use these extra logs using some HIVE case studies, and then we will draw some conclusions.
Yeah, good to mention that we accept questions during or after the presentation, as you feel.
Yeah, that's right. Thanks, Stamatis. So query planning shares a lot of commonalities with general software. Calcite is running on JVM, so we will be using JVM terminology. But in general, when you have an out of memory, you can investigate it through heap dumps. When you have other issues like stack overflows, unresponsiveness, and general runtime crashes, you might want to take a look at stack traces. Specifically for query planning, when you have wrong results, you will investigate what happens in your plans. But many times the root cause is in the rule-based transformation. And good logs are key for finding this root cause, as we will see. Another way to, let's say, to investigate issues is interactive debugging, but that's not always feasible because sometimes the failure happens in CI or it's in a customer environment with restricted access. Sometimes the problem is data specific. You don't have the enough data or the full data specification to really repro the problem. And even if you do, debugging planning issues without using logs is challenging. Why? Because we have complex transformation logic and a large number of transformations that are also creating a lot of intermediate objects. And last but not least, transformations are applied multiple times. So it's really hard to put a breakpoint, even if you know in which rule the problem is happening.
So yeah,
now Stamatis, yeah, go ahead.
Yeah, before moving to
you are muted, I think.
Okay, is it good now?
Yeah.
So yeah, I was gonna highlight a bit that it's always good to do interactive debugging, like you have a problem and you fix it. But the truth is that in real production situations, you don't get to reproduce a problem. So usually you have a problem coming from a customer, for instance, and you have zero access to their system. So they describe you what happened, they may send you the query, but the truth is that the problem may be very likely is data specific. So it means that you cannot even reproduce the same plan on your own environment. And in that case, you cannot really do interactive debugging. And then most of the time, what will happen, let's say, if you get an out-of-memory error in a system, in a DBMS, there are many places where this might happen. So somebody gets an out-of-memory error, they send you the stack trace, potentially a heap dump. And yeah, all good systems have logs, but all logs have different granularity. So the first person or the persons that will come to get to the heap dump or or the stack trace may be completely unrelated. And also the heap dump may not solve the actual problem that comes from the planner. So knowing that some logs in particular, we are talking about Calcite logs, are present and how to use them is very, very crucial. So the main building logger that we are going to talk about today is the RuleEventLogger. As the name indicates, it prints a lot of information when a rule matches and what it produces. So before we actually see what it does, it's good to see how to enable this in a system. So this particular example is about shows how to do it with log4j2. Obviously, if you are using another system, you have to configure things slightly differently, but hopefully the ideas remain the same. So this is a very basic configuration. So you have on the top, you see that we have an appender that basically prints stuff to standard output. And if you check the pattern layout, you will only get the message, the log message, and a new line. So basically the bare minimum. And then you have the reloft planner logger, which is also using the RuleEventLogger that we are talking about here. And you can see that there are various levels of information. You can set it to info, but what is more interesting when you get a planner problem is to set it to debug. So when you set it to debug, you'll get a lot of information on how to approach the problem. And then the next part that is quite the newest stuff that was introduced rather recently, so Calcite 129 and 130, is the full plan marker. So this marker makes things a bit more verbose, but as you'll see afterwards, it's quite useful. And then depending on again which actual logger implementation you use, you have to see how to configure it. So for log4j2, you put a log4j XML file or another syntax in your class path, and things will work. So in order to make things a bit more easy to see with an example, you can play out with Calcite unit tests. So if you add the configuration that is shown here to under test resources, and you change the level to debug, you are going to see what's the actual output. And here is how you will configure the logger with a property syntax. So log4j has different kind of syntaxes. People tend to prefer one or the other. I tend to prefer the XML because it's much more easier to grasp, and the hierarchical nature of the logger is much more of the log4j. It's much easier to express in XML. But for those that are using the property syntax, this is how you can express the equivalent stuff. And why I'm mentioning this in particular is because HIVE, for instance, uses the property syntax. So if you want to see how to do things in HIVE, you have to know how to do it with the property syntax. And since we are going to see case studies of how we solve cases using logs in HIVE, it's also good to show how you actually enable this thing in HIVE. Most of the things are exactly identical as you would enable things in Calcite, but bear in mind that in HIVE we are a bit we are in an older version of Calcite. So currently the Apache master in HIVE uses 125. So we don't have all the new marker things that were introduced in 129 and 130. So this particular Jira in HIVE kind of introduced a copy-paste of some classes in HIVE to do the same work. But the configuration part is exactly the same. And if you are interested in playing with HIVE test cases, then the HIVE log4j properties file is the way to go, the place to add the configuration. So let's see how this actually looks in practice. So I took a very, very simple example from the Calcite unit test suite. It's rel opt rules test aggregate remove. And then I switch, for the moment, let's assume that we don't have the full marker. So we just have the plain default logging. If we enable the debug logging and we run it, what we are going to see in the standard output is this one. So the logs are pretty straightforward to understand. So here on the left, you have the call ID. So basically, this shows how many rules were attempted or applied in total. So for these test cases, it's basically pretty simple. So we have only 3 rule applications. And then obviously on the core, we have to know the rule that did something. So there are 3 rules that are launched in this unit test, which is aggregate remove, project merge, project merge rule 2 times. And we have obviously what goes to the input of the rule. So which exactly relation operator matched the rule. So here we have a logical aggregate. And we also have the production. So we can see that the aggregate remove rule at the beginning matched an aggregate and produced a project. So this is already quite useful, as you will see in the sequel. But actually, we don't know what exactly the rule did. So we know that it removes the aggregate, but in other cases, we know that it merged a project. But what exactly it did, we don't know. And this is quite important to understand some problems, as we're going to see next. So what we can do in this case, we can make the logs a bit more verbose. So we can change the full plan marker, the onMatch property, to accept. And if we do this, we're going to have a more verbose output. And as you can see now, for the call number 0, so for the first rule, we can see the full plan for the input. So we don't see only that it matched an aggregate, but we can see that it was a group of two columns, 0 and 1, which is employee number and the type number. And we can also see that it was a count. So again, this is a bit trivial because we see the query right there. It's very simple, and maybe we could infer many of this stuff. But when things get more complicated, as we are going to see right next, things are very, very important to have a bit more information. So let me start with the first, let's say, case study. And the symptoms here is that after, this is about Apache HIVE upstream in master. So there was an attempt to upgrade the Calcite version from 125 to 133. And the reason I picked this example is because I tried to do it rather recently, so I have everything fresh. So when I begin, let's say, doing a Calcite upgrade, I like to run a TPC-DS suite that we have, so that I can verify that how the plans changed and what is important, what is not, and things like that. And this suite usually takes a few minutes, like maybe 5 to 10 minutes. And in this case, it was running forever. So something is definitely going on. And I was thinking that some queries are taking very, very long time. Then I realized that they were actually hanging. But at the beginning, I thought that they were very, very slow. So the query was like various queries had this behavior. So I started with looking into query 13. So there is nothing particular to understand. I mean, I'm showing the query here just to get a rough grasp of how it looks like. It's a join of 6 tables with a few aggregates. And then there are quite a bunch of filters. And yeah, I'm only focusing a bit to mention that there are a few disjunctions that are taking place. So we want, for the customer demographics table, we are looking in marital status of married people, divorced, and I guess U is for unknown. And I'm highlighting this because we are going to see it right after. So I have this query, and it's running basically very, very slow, let's say. So we want to see why does it take so long? Where is it stuck? What does it do? Of course, yeah, we have to gather information. And if this was a customer problem, we'd have probably to take the same steps. So when we want to see why a query takes so long, like the first, I guess the first reaction is to profile the application. Like, I want to see which method, which part of the application takes long. So yeah, let's say that we use a async profiler for that one. I guess you can barely see the flame graph on the right for this query, but what is worth seeing is that it is big. It has a big stack, and it's basically pruned because I couldn't fit this nicely into a slide. And maybe for if somebody very familiar with Calcite can understand that there is a call to heap planner, and then you have a depth first apply many times. Okay, so yeah, I guess for Calcite devs or committers, they may understand almost immediately that, okay, the plan is getting big. So, but yeah, the stack trace is still pretty big to be actually a real valid plan. So another kind of quite instinct reaction is to collect the stack traces. So using JStack, for instance. And this happens quite common in general problems when the server is hanging. People are instructed, or support people are instructed to collect stack traces. So if you collect stack traces, in this case, let's say I took a stack trace, you see that it's again huge. So you have a stack trace, which is 2,000 lines. And it's basically the same thing repeated over and over and over again. So you have a call to RuleMD predicates, and the same pattern appears like 2,000 times. And yeah, first thing to note is that usually the JVM has some limitations on the stack depth. So even if you take a stack trace, you don't see where it starts. So you see that it's all full of RuleMD predicates, but you don't know where has this started. So now, okay, yeah, we have the lines. We are lucky, and using the stack trace plus the actual code, we can actually infer that the plan has more than 1,000 nested filter operators. So yeah, we have, even with the stack traces and the profiler, we have advanced quite a bit into the debugging. So we know that there is a problem with the filter operators. Now, yeah, who creates the operators and why? Why does it happen? We still don't have the root cause. So that's why I'm saying that logs are important, and in particular, the RuleEventLogger logs are very important. Obviously, there are other logs that are also important, but for CBO problems, for Calcite problems, these are quite useful. So I cannot actually show you the log file completely because it's quite messy. But let's say that I'm searching for this particular, I enable the logs as we have seen in the beginning, and then I grep for the 10 lines following a rule production. And here is what I see in HIVE. So as you can see, like I have the first 3 calls, the first 3 rules that are matching in these TPC-DS queries. And I see that there is a rule called the HIVE prefiltering rule that is producing a HIVE filter. Okay, yeah, I mean, the structure was saying that we have 1,000 filters, so seeing a filter here is quite useful. And the second rule does again generates a HIVE filter, and the third rule generates a HIVE filter again. So if I go all over the place, I mean, this is quite easy to see actually when you're browsing the logs, because when you start checking the rules and the productions, and in particular the full plan, as you can see here, you start seeing the pattern. So you see immediately that there is a HIVE filter introduced over and over again. And if you go down your screen, you'll see that the screen, the logs are getting always a bit on the right. So it's very, very easy to spot that there is something really, really bad going on. And it is very, very easy to see even just from the logs. So you open the logs, you start going through them, and you, from the first or second rule, you start thinking that these are not going well. And yeah, with spending a few more minutes on this screen, you may have noticed already, you may observe that the filter condition is identical. So obviously, because I cannot fit everything in the slide, I have pruned the rightmost part. But you can see that the same filter is generated over and over again. So, okay, root cause found. The problem is HIVE pre-filtering rule, and it basically matches infinitely and creates identical filters multiple times. So now, if we have an actual repro, we can get more information. And this is where interactive debugging, yeah, I mean, we cannot avoid it. Logs do not save us from attaching the debugger or solving the problem, but they can easily get us to the root cause. So as I showed you, there are many disjunctions in the query. And the whole thing starts from an OR condition where you have the marital status, and you say you are searching for married, divorced, and unknown. And the rule does something quite interesting. So after some time, so the rule tries to push some filters down in a kind of redundant fashion. But in order to essentially avoid this infinite rule problem, what it does, it says that, okay, I have this OR condition. So I want to check if my inputs, if the operators below contain already this condition. If they do, I will not do it because, yes, it will lead to infinite rule matching. So this is kind of a way to prevent this. I'm not saying that it's a good practice or bad. I'm just stating what the rule does. So, and the rule internally, this part of the rule relies on the built-in metadata providers in Calcite that, in particular, they get pulled up predicates. So we are checking the pull up predicates to see if it contains the OR that we have seen above. And yeah, I mean, after a bit of debugging, I found out that it never actually returns an OR. It will return a search operator, which is equivalent, but the rule does not even do equals. It does some kind of string matching. So you check the string of with OR and the search, and you see that they don't match. You say, okay, cool. I don't have the OR, so I will push it. So, and this is what it does. It pushes the OR and it does it arbitrary many number of times. So, okay, I mean, showing how the logs work is already interesting. Just for the sake of completeness, this was like difference in behavior when you upgraded from 125 to 133 was mainly due to two things. So the first one was the addition of the search operator and the search literals, which is a good thing because there is a uniform way of representing stuff. In this case, we can represent OR as a search operator. So search is trying to do that, but Hive didn't know about this. So essentially now we have have to fix it somehow. And the second reason is because in this Calcite 5036, there were some additions in get pulled up predicates that are introducing some additional simplifications. So I'm thinking that if the simplifications weren't there, the OR wouldn't change into a search, and probably the problem may never appear. So these together kind of triggered this infinite rule problem. But luckily, with the logs, we were able to find it quite fast. So yeah, now I will give the mic to Alessandro to continue with the rest of the Hive case studies with the next two.
So thanks, Stamatis. So yeah, in the rest of the presentation, we will keep relying on this logging format. So let's take a moment to have a closer look to this format. So we have already seen that the produced keyword is used to like identify rules that are successfully applied and they have produced something. So the output format goes as follows. You have the code number, you have the rule description that's in square brackets. Then you have the rel number of the rel that is created, followed by its rel kind. So in general, in the logs, when we spot that something is not wrong, we can follow these rel numbers around. So if we see that a given one is bad, it doesn't look right to us, we can check where it was produced and which call number introduced it. This greatly help to place conditional breakpoints. So when you know the call number and the rel number, and of course the rule that is producing it, you can place a conditional breakpoint and stop exactly when this rel is produced. So we will see two other kinds of like common planning issues. The first one is out of memory at planning time, where you have a sequence of rule applications that is looping from a certain point onwards during the query planning process. So if your database system based on Calcite has a kind of an explain command, you usually want to run it, get the logs, and visually inspecting the list of rules that were applied by grabbing the logs as shown in the previous slide. Usually it's pretty simple to see it, like really visually. And when you have this list, you want to find the first occurrence of this list of like looping rules. And yeah, the most natural thing to do is to start analyzing the plans that were generated right before and after it to see if something is already off. A note to this is that the rel triggering the loop and the plan that you know is causing this issue might have been created outside the sequence. So the symptoms might appear here, but the real root cause could be elsewhere. We will see an example coming from a Hive ticket. We have a rather simple query with an equijoin from this table test 3 and a subquery with a union between two test tables, test 1 and test 2. So it looks rather simple. The symptoms of the issue we had was an out of memory, as mentioned. And what we could notice in the logs immediately was that there was a filter that was becoming increasingly big. So more and more complex and bigger and bigger in size until memory was exhausted. So after 20 rule applications or so, the query plan associated to the join was looking as follows. So we can see the this table scan for table test 3 and the subplan associated to the union where test 2 and test 1 tables are scanned. So here we have some is not null predicates that were created by looking at the table definition that were already in a sense pushed to the left-hand side of the join. We also have a filter that is coming directly from the query. From the logs, we could see that this was the sequence of rules that was in loop continuously. And what are those rules doing? So there is the first subsequence of this list that is pushing predicates from the right-hand side to the left-hand side of the join by means of the HIVE join push transitive predicates rule. That is very similar in spirit and in implementation to the join push transitive predicates rule in Calcite. And the same goes for the converse from the left-hand side to the right-hand side. Then there are some more steps, some more rules that are applied that are trying to push the filters all down and merge them with the existing ones. So with all these in mind, let's have a look at the genesis of the issue. So as we have mentioned, there are two filters in the two operands of the union. At this point, what the rule is doing is to leverage the metadata provider and specifically the ReLMD predicates metadata provider to try to infer predicates from the left-hand side. Given that there is a union all, the two filters are put together, are stitched together with an OR, with the disjunction. So this new predicates is pushed to the right-hand side of the query, and at this point, since we have a filter on top of a filter, the HIVE filter merge rule will combine them with a conjunction. So at this point, the is not null should be simplified because both operands of the OR are equalities against expressions that should allow this is not null to be removed. But this was not happening in the version of Calcite we had. So this simplification opportunity was missed. And at this point, what happens? So the idea is that this push transitive predicate rule tries to reach a fixed point where no new filters can be inferred. It keeps a state where all the filters that have been inferred and pushed transitively are stored, and it relies on reaching a state where no new filters can be inferred. Since we are missing simplification opportunities at this step, this fixed point is never reached because what happens is that the newly created filter will be again pushed to the other side. At this point, since we couldn't simplify it and we are adding more and more logical operands ending with some other predicates, we won't be able to simplify it further. And so this keeps going on, and we have filters that are growing, and this is still a rather simple one, but it will keep adding more and more complexity until it blows up memory completely. So what the logs could tell us immediately was that the filter didn't look right. This looks like pretty bad already. Filters were at the end were like hundreds, if not thousands of operands. So we could see that there was something of using this information with the plans that was produced rather early in the. So I'm referring to this plan, and the list of rules that were applied. We could easily infer where the problem was lying, and so addressing the root cause in this rule. So another kind of issue that is pretty common in query planning is incomplete or incorrect plans. Again, this usually boils down to identifying the first rel that looks bad or that we can be suspicious of. And by looking at the rel number that we have seen is printed in the logs, we can trace it back to the part of the logs where this rel is produced, and also understand which rule is producing it and at which call. So at this point, the resolution of the specific issue highly depends on the nature of the issue itself, so there is no magic formula here. But using the logs in the way we have mentioned, we can get a call number and a rel number. At this point, if you have a reproducer available, you can easily place a conditional breakpoint. So this alleviates a bit the issue of having the same rule applied multiple times, and you don't have to like skipping the breakpoint over and over again until you find the sweet spot. You can fast forward to the right call of the rule. So there is another example coming from a HIVE ticket where we had some incomplete plan with missing results. So we can see the KO version of the query to the left and the OK version to the right. Below, we have the associated plans. We could immediately see that what was missing in the KO case were the rows that were contributed by the second operand of the union all that was completely missing in the KO case. So the first reflex was to have a look at the rules that were applied. And we were lucky enough in this case, of course, after reducing the reproducer to a minimal state, to see that the rel kind produced by the very second rule that was applied was different. So we have a HIVE union in the OK case and a HIVE filter in the KO case. Since we are looking at the HIVE union that is disappearing, it was pretty obvious that the root cause was in a HIVE filter setup transpose rule. Since we were not familiar with what this rule was doing, it was not very intuitive for us to have some pruning logics in this rule, but actually looking at the implementation, this is what the rule was doing. So there was some logic based on simplification to check if one of the two union all operands was not contributing any rows and pruning it. So the problem was finally a bad way to call rec simplify. So we could simply fix the way it was calling it and remove this, let's say, false positive that was leading to having an incomplete plan and fixing the issue. So we have seen some common planning issues. Another rather useful tool that we have coming from a built-in Calcite that we have leveraged in HIVE is this method from the abstract rel planner class that's called set rule desk exclusion filter. what it does, it allows to exclude rules based on a regular expression over their description. The description is meant to be unique, so it can be used in this way. So these rules are not used by the planner, even if they are registered. So we advocate of the benefits of having a configuration that is ingesting this kind of regular expression for the following reasons. So having a kind of a configuration that can like prevent using some of the rules, it avoids recompiling. So we can troubleshoot in a much faster way and test out hypotheses. It can also be a quick workaround to customers. So when you have identified which rule or which rules are faulty for a given query, you can just kill them with a property that can be activated per query. So it doesn't have to be a global parameter. And it's definitely less invasive than disabling cost-based optimization altogether. So for other downstream projects that are built on Calcite, if you are curious to have a look at how this is implemented in HIVE, you have the reference of the ticket and an example of how this property can be called. We haven't been adding much to it. We are simply calling this rule, but the intuition behind creating this configuration property can be useful. So this brings us to the conclusion. So we have seen that many planning issues finally boil down to rule transformations, making the plan bigger and bigger. And we also have seen how the built-in loggers can help you troubleshooting more easily. These logs are configurable via XML or property files for log4j2 implementation. And they are also, they have a verbosity that can be configured as well. So we have also seen some common pain points in query planning that's stemming from the richness of SQL on one hand and of our internal representation on the other, that is using multiple equivalent operators, for instance, or search and in are an example, but also that many rules are pushing and pulling predicates with different strategies and some inconsistencies around simplifications, because some rules they use rel builder, which simplifies immediately. So some others they are using factories. Some are doing some simplification explicitly, some others don't. So there is some like inconsistencies that can lead to issues. Finally, we have seen how to use this method coming from a ReLog planner for providing quick workarounds and verify hypotheses. So this concludes the presentation, and you're welcome to ask questions if you have any.